squared itself as W1 times mu1 squared sigma 1 squared plus 1 minus W1 mu2 squared plus sigma 2 squared. And each of these quantities is at least epsilon. So we can write this out as at least epsilon times mu1 squared sigma 1 squared. See, all this quantity is, it's the expected value of x squared conditioned on it coming from the first component. That's explicitly what the square is. We have to add in the square of the mean, and then we add in the variance. And the same way, we can just lower bound W1 and 1 minus W1 by epsilon. And this proves the claim, because we know this quantity is 1. So all of these parameters are appropriately bounded. None of the variances can be larger than 1 over epsilon, because if they are, then the overall variance of the mixture would be larger than 1. The same with each of these means, they can't be larger than 1 over root epsilon. So this is great because it means right now the problem should look very, very simple, right? Because we have 5 parameters, the mixing weight, the mean and variance, and the mean and variance. And each of these parameters are actually bounded in some nice range. So at first glance, you would think that what you can do is grid search. Now, grid search is going to work, but there's actually much more of a story to it. So let me write out what grid search means in this context. I'll tell you a simple statement about it, but then the bulk of the class we're going to be proving a much more interesting statement about it. So let me define by what I mean by grid search, and let me define it as general as we'll need it. So it'll be parameterized by some values, n, k, c1, and c2, that define how exactly we perform the grid search. One of these parameters is just how many samples we take. So we take samples, x1, x2, and so on, up to xn, from f of x. So we're defining a grid search. One of its parameters is just how many samples we need. And as usual, in Pearson's approach, for example, do exactly what we did there. We compute the empirical means. And we do it for the first k moments. So in Pearson's approach, he did it for the first 6 moments. That's actually the setting we're going to use. But let me state the grid search more generally. So we take the first k moments, and now all we do, we look over all valid settings of parameters. So we look at any theta in this grid. We look at the range of possible values for its mixing weight, so between epsilon and 1 minus epsilon. We look at the range of possible values for the first mean and the first variance. Oops. Same with the second mean. And the second variance. And what we're going to do, we're going to assume that each parameter is an integer multiple of epsilon to the c1. So we have to search over this continuous space, which is bounded, but we're going to do it at some granularity, epsilon to the c1. So that's one of the other parameters. The only thing I have to do is define c2, which comes in with every setting of parameters here that corresponds to a valid mixture of 2 Gaussians, at least in the normal form we've assumed it. Well, we have to decide whether or not it matches close enough to the empirically observed moments, and we're going to use C2 for that. So if for all r, 1 to k, we have that mr hat minus mr theta recall that this is the analytic prediction for what the RF moment should be if these are the true parameters. If this is at most epsilon to the C2, I'm actually going to divide this by 2 for reasons that will be clear later. Then we output theta, and we grid. So that's it. This is grid search. As we do the natural thing, we have each of our 5 parameters is bounded in some reasonable range, and we compute the first k moments with n samples, so we have some guarantee that with high probability each of these empirical estimates is close enough to the true value, and then we just find any discretization of the parameters that's close enough up to some tolerance epsilon to the C2. So this is grid search. Are there any questions about grid search?
So if the line is too small, then we don't have a solution.
Yes, exactly. So there's going to be something that's easy that's true, and you're absolutely right that that's a complication even with the easy part of this direction. And there'll be something which is vital, which is not so obvious. So let me state the easy part first, and this will exactly get to your question. So let I'll let round epsilon C1 of theta be any point in the grid that's component-wise epsilon to C1 close to theta, right? So just working up towards your question, if we have some true value for these parameters, we have some natural guess for what should be the point in our grid, if any, that passes our test. So what we do is we just discretize this point as best as possible. And your point is that we certainly need the discretization to be fine enough so that it can possibly pass this test. And we also need that the number of samples is good enough that this is close to how close the empirical average is to the true average. These are all true statements. Let me write up the easy part right now. So the way I'll phrase it is the following, but I'll leave it just as a claim. We won't prove it. So the way to think about this is that we have this test defined by the first k moments and defined by how close we want the what our tolerance is. So no matter how tight you make this test, no matter how stringent it is in terms of how large k is for it being a fixed constant, no matter how stringent you make this for C2 being a fixed constant, there is some setting for taking a polynomial number of samples and for some target discretization C1, which the natural point will pass the test. So that's the way to think about your question, is that you should choose the gridding after you choose what your tolerance is and what k is. So this is all fine, but let me state it. So for any k, for any epsilon greater than 0, for any C2 is constant. So these are how stringent I make my test, how many moments on which you have to agree, and up to what accuracy. Then the claim is that there is some constant, 1/epsilon to the C1 size gridding, and poly number of samples. So we'll take n to be some fixed poly in 1/epsilon, where this fixed poly depends on k, depends on C1, depends on C2, and so on. So that with high probability, the natural rounding passes the test. This is the easy part. So does this claim make sense? This is the easy part. It's just that we have some natural candidate point, which is our closest in our grid to the true parameters. And if we have a good test, we definitely need that this point that is the closest in the grid should pass our test. And you should choose the gridding after you've chosen how stringent you want to make the test. Because otherwise, if you chose too coarse a gridding, then you might not be able to pass this test. So this is the easy part. This is oftentimes called completeness, just that the setting of parameters that we're interested in, the natural rounding of theta to a grid point, actually does pass the test. Now, I claim, though, we're not done. I mean, we have a lot of time left in class today. So what's the issue with this? Why can't we just use this as our univariate algorithm and call it a day? Any thoughts? Yep.
Well, you have to show you don't have tons of other junk passing the test too.
Exactly. So this is called completeness, just in complexity theory language. And the hard part is to show soundness, that there's no other spurious grid point that passes our test. Why can't there be a completely unrelated grid point that has nothing to do with the true parameters that somehow magically agrees close enough on each of the first k moments? Put it another way, that this claim makes sense regardless of what I choose k to be. If I choose k to be something small like 4, then there'll definitely be another setting of the parameters that explains the first 4 moments that has nothing to do with the true parameters, just because I have 5 degrees of freedom in how I choose what the underlying parameters are. So the main issue in all of this is to show soundness. So let me tell you the main lemma, which we're going to prove actually what's the major special case of it. I mean, it's a bit involved to prove the full lemma, but we're going to prove a special case which contains almost all of the main ideas today. And so the main lemma is really just soundness as a proof of correctness, that if I run this grid search with the right parameters, I necessarily find something which is close to true parameters. There's nothing else that can pass my test. So the way that I'll state this lemma is if f and f hat are both in standard form, so they both have this property that their mixing weights are between epsilon and 1 minus epsilon. They're both normalized to satisfy these conditions. And both of the two mixtures are such that their components are bounded away from being identical. That we have a lower bound on the parameter distance between component 1 and component 2 in F, and a lower bound on the parameter distance between component 1 and component 2 in F hat. So if all of those standard form conditions are met, and if they're not close to each other, so if the min over all permutations from 1 to 2, so matching component 1 to which of the components in F hat, if we have the following property, this will be a little bit of a mouthful, but let me explain it in a second. This is the key lemma. That's going to be the proof of correctness. So what we want to say is that if we have these f and f hat that meet the conditions we've assumed, and that we can assume are true about the true parameters we're trying to learn, so they're in the standard form that I described above. And moreover, if f and f hat are just identical mixtures, they have the same parameters, then we have no hope of telling them apart because they're the same. Even if there's a way of interchanging which one's component 1 and which one's component 2, then again, we have no hope of telling them apart. What we want to say is that if f and f hat have some reasonable parameter distance between them, that there's no matching between their components, components in one of the mixtures and components in the other, so that across this matching, you get all of the mixing weights and the means and the variances right. If this minimum is at least epsilon, the parameter distance is at least epsilon, then we want to say that there's some low order moment that has a noticeable discrepancy. So this sometimes I'll refer to as parameter distance. And what we really want to say is that parameter distance translates into a distance that we can realize and measure. That parameter distance is polynomially related to discrepancy in moments. And moreover, that we don't have to go to too high a moment to actually realize this discrepancy. Right? So this is the main lemma. Are there any questions about this lemma? Yeah.
So is it saying there exists a C2 for which this is true?
Yes. So some universal constant, C2. I think in our case we proved 70. So it's not very good, but it's a constant. Are there any other questions about this, the statement of it?
So most of them has to be standard form.
Yes.
But then it doesn't include cases with one of them.
Right. So what you would really do for this grid search is now I would, instead of searching over all theta in this range, which have a valid discretization of the parameters up to epsilon C1, I also need to constrain that and theta is in standard form. Really, you just need it to be close to standard form. So you don't need that its mean is exactly 0, but you need that its mean is small. You don't need that its variance is exactly 1. You need that it's close to 1. But you do need that, every theta that you try out, you need some lower bound on the parameter distance of its two components to each other. That's something which holds for the true underlying mixture. So what we really want to say is that we have samples which came from the true mixture, which we know is in standard form, and we're comparing them to a hypothesis that's also in standard form. And we want to say is that the only way that you can get two standard form things to agree with each other up to some target accuracy is if they actually are close in parameter distance. So the way to think about this is this lemma is useful actually in the contrapositive form, because it tells you that if you are close enough according to the first 6 moments, that can't be an accident and that you really must have your parameter circlets. So this is the main lemma. The easy part is the completeness, the hard part is the soundness. So let me assume this lemma, and let's see why grid search works. I mean, it's very easy, but let's just make sure we have, all of our I's and T's dotted. So let's take k equals 6 and n equals poly in one of our epsilon samples. in our grid search so that, actually let me do the following. Let me call this theta hat, theta hat, theta hat. So that throughout today, we're going to think about theta hat as being the hypothesis that we want to prove is close to the true parameters. And I'll always use theta to denote the true parameters of the underlying mixture. And what will be true is that if we take enough samples, we take poly-n 1/epsilon samples, once we fix the number of moments, we'll have the property that the empirical moments are indeed close enough for each of the first 6 moments. So all we do is we've chosen our 6th moment test. We're following Pearson's approach, just a slightly different variant. In Pearson's approach, he used the 6th moment as a tiebreaker. And here we're explicitly putting it in as a 6th extra constraint. Now, once you've chosen, you want to look at the first 6 moments, you take some poly-n 1/epsilon samples so that you're close enough to those true parameters. And C2 is whatever C2 is in the main lemma. It's just some fixed universal constant. It's 70, right? And then if some valid theta hat passes the test, and is in standard form, we're assuming the same thing about theta, then we know that MR of theta hat minus M hat is itself epsilon to the C2 over 2, again, for all R from 1 to 6. But all of this together implies that the moments of theta and theta hat both match. Within epsilon of the C2, I just lose a triangle inequality over these two. And what this together implies is it implies that theta and theta hat are epsilon close in parameter distance. So that's it, right? We have the simple claim that once we've chosen K and C2, that we can choose some fine enough gridding, C1, so that the natural candidate solution, where we take the true parameters and round them, will pass the test. That's the completeness. And the soundness follows now. It's just that once we've chosen what our test is, we've chosen K equals 6, we've chosen C2 from this lemma, then all we have to do is we take a polynomial number of samples, and what will be true is that anything that passes our test, whatever it is, whether it's the thing we're expecting or it's something different, it has to have the property that it's close in parameter distance to the true parameters. Because there's nothing else that could possibly satisfy the first 6 moments up to that target accuracy. So this is the proof, right? All I have to do is prove the main lemma. Actually, I'm going to prove a special case. So are there any questions about this? So it's very easy to look at the grid search and just see the simple claim and think that you're done. But the issue is you always have to worry in some of these learning problems where you're trying to learn the parameters. Why can't there be 2 very different settings of the parameters that explain all of the empirical things I'm measuring about the data? That's something that you really do have to worry about. And it's a question which is a purely information theoretic question. It has nothing to do with algorithms. And that's exactly the type of thing we need to address in this main lemma. So I think it's kind of funny, and I'll elaborate on this maybe some other time, but there are a bunch of settings in learning where the algorithms we're looking for have statistical consequences that sometimes I don't know in their own right. If I gave you an algorithm for learning the parameters of a mixture of two Gaussians, which was guaranteed to learn them within some epsilon, then it would necessarily imply some sort of lemma like this. It would imply that there cannot be two different settings of the parameters that are epsilon different that produce almost the same distribution. The difference is here we're actually using just the notion of distance in moments, which is a weaker distance than things like total variation distance. So I might elaborate on that later. But actually what I'm going to do is I'm going to prove this lemma. Is there a question?
Yes.
Yeah.
But conversely, how do we know there is at least one parameter that will satisfy?
Yes. So if you think about this claim, see, once you've chosen K and C2, then the point is that there is a C1 so that the natural rounding passed the test. All you need is that if you change the parameters by epsilon to the C1, you don't destroy the moments too much, more than epsilon to the C2. So those two things together apply. If this is the completeness, that's the soundness. Make sense? Any other questions? All right, so actually the way that we're going to prove this lemma is, see, this lemma is a quantitative statement about how parameter distance implies a lower bound in this moment distance, the first 6 moments. Actually, what I claim is it's not even obvious for epsilon equals 0. So what if instead I have the property that each of the first 6 moments are exactly the same? Epsilon is 0. I have that it's at most 0 here. Why does that imply that my parameter distance is 0, 2? This is a special case of this theorem, of this lemma in the contrapositive. That's what we're going to prove. So let me state that more precisely. I have space here already. So the main question which we're going to answer today do the exact first 6 moments of a mixture of two Gaussians exactly determine its parameters. The way to think about this is the same thing that was worrying us about the grid search, that there could be some other spurious point. You know, if the answer to this question was no, then this test is just doomed to failure, right? Because it would mean it doesn't matter how close you get your empirical moments to the true moments. There just flat out is a completely different explanation, which has nothing to do with the true parameters, that exactly replicates the true first 6 moments. So this is the special case that actually contains almost all the main ideas. To actually prove the main lemma, you know, you need a lot better quantitative estimates, but it follows the same outline. So I'm going to prove this to you, that the answer is yes. So are there any questions about this? All right, let's do it. I am definitely running out of board space already. This stuff up for the time being. So can I erase this? So first, I'm going to take this question, I'm going to reduce it to a much simpler sounding question. So let's take h of x to just be f of x minus f hat of x. So we have the density function for the first mixture of two Gaussians, and we have the density function for the second mixture of two Gaussians. And all we want to do is we want to prove that if these are different density functions, but they're both mixtures of two Gaussians, that they necessarily have to differ on at least one of their first 6 moments. That's what we want to prove. And all I'm going to do is I'm going to take this function on the real line, which integrates to 1 and is non-negative, and I'm going to pointwise subtract this function, which is, integrates to 1 and is pointwise non-negative. So all I get is I get this function, h of x, which can take positive and negative values. And I claim that actually the heart of the argument is on understanding how many times h of x crosses the 0 axis. That's the entire point. So let's state it conditionally. What I'm claiming is if, and this will be the part that we still have to prove, if h of x has at most 6 0 crossings, then there is some r that realizes the difference. So this is what I wanted to prove, right? And I'm going to assume for the time being that we have this property that h of x crosses the 0 axis at most 6 times. This is a statement which actually has nothing to do with mixtures of two Gaussians. It's just that if h of x crosses at most 6 times, then I can realize the difference between them by a low-degree polynomial, and that itself will give me that one of the first 6 moments is different. So this has nothing to do with mixtures of two Gaussians, but proving this part will. In any case, let's prove this part for the time being, that if we can prove h of x crosses at most 6 times, then we're done. So the way that we can do this suppose z1 to zk are the 0 crossings. And k is, of course, at most 6 by assumption. Then what we can do is we can explicitly write out a polynomial, p of x, which we're going to choose the sign of it appropriately, so that in such a way that it agrees with the sign of h. Okay? So that's the idea, is that we can explicitly write out some polynomial which has this property that everywhere the sign agrees with what the sign of this underlying function is. The way to think about it is h of x crosses the 0 axis at different points. All we're doing is we're explicitly putting down zeros at those points in such a way that we're enforcing that p actually crosses the 0 axis there too. To be more precise, if sign of h of x is 0, then I don't actually care about it. So I'll just say for all x where sign of h of x is non-zero. Now, it can be shown that the integral of p of x against h of x is strictly greater than 0. So the way to think about this is that you have some p which agrees with the sign of h of x everywhere. And so this integral certainly can't be negative. Now what you have to do is you have to make sure that it doesn't have 0 contribution. If you just agreed with it on some measure 0 set, that would be bad, but it's really just the smoothness properties of h of x that enforce that any p that you have this way correlates non-negligibly differently with h of x. So that's the important point, but that's actually going to imply the entire lemma that we're after now. Because now what we can do is we can write p of x, because it's a low-degree polynomial, explicitly the way we've constructed it, and just write it out as sum from r equals 1 to k of pr, so that's the rth coefficient of x to the r. And then we have the property that the absolute value of the integral of p of x, h of x dx, minus infinity to infinity, is by triangle inequality at most this quantity. And now, can anyone tell me what this part is?
Difference in the output.
Yes. I guess let me say it's the absolute value, but exactly, right? So it's mr of theta minus mr of theta hat. That's great, right? This quantity is strictly greater than 0. And if you really did agree on the first 6 moments, the right-hand side would be 0. So that would be a contradiction. That implies it. Right? So as soon as h of x has some simple form that it doesn't cross the 0 axis at most 6 times, then it implies that one of the first 6 moments is different, because we can explicitly construct this low-degree polynomial that correlates differently. Now, if you want to prove the real main lemma with all these quantitative bounds, then you would need to be careful about how non-zero this p of x is, and what you're actually implying about the difference in one of the first 6 moments. But this is the heart of the argument, is just in showing you have at most 6 0 crossings. Right? Let's prove the last part. So we've reduced this high-dimensional learning problem. We're in n dimensions with mixtures of 2 Gaussians, which are heavily overlapping. Over the last lecture, we reduced it carefully to a sequence of 1-dimensional problems after we paired up all the different components and set up a high-dimensional linear system. Then in 1 dimension, we talked about a grid search, and we reduced our problem to showing soundness. And in all of this, we just cared about epsilon equals 0 for the soundness. And now we've reduced it even further to just the simple sounding question of I take any mixture of 2 Gaussians and I pointwise subtract any other mixture of 2 Gaussians. Why can't the function cross the 0 axis too many times? Why should it be a simple function? So let's prove that last part. In fact, let's prove it more generally. I'll call this the 0 crossing lemma. So let's say that we take any h of x, which is some linear combination of t Gaussians with coefficients alpha sub I and parameters mu I, sigma I squared, x. These can be positive or negative. And really the case that I cared about was the case where t equals 4, and I'm adding 2 Gaussians and I'm subtracting 2 others, right? and I wanted to prove that it has at most 6 zero crossings. Let me more generally think about any linear combination of T Gaussians. And what I want to prove is that if h of x is not identically 0, that would be bad, of course. But that would also mean that the two mixtures are exactly the same, and they have the same components, so that's fine. If h of x is not identically 0, then there are, at most, 2t minus 2 zero crossings. So in the special case of t equals 4, this implies exactly what we're after. 6 moments suffice. That's the epsilon equals 0 case of this main quantitative lemma, which proves correctness for the grid search problem. And what I want to do is I want to prove it more generally for any t that we get at most 2t minus 2. So does this lemma statement make sense? All right, and we're going to prove it by induction. Once I give you some key facts about Gaussians that we're going to use. And to keep it simple, let me just assume it's true for t equals 3. And we want to prove the t equals 4 case. So we know for t equals 3, the number of zero crossings is at most 4. And what we want to do is we want to use that fact that it's true for 3 with linear combinations of 3 Gaussians with at most 4 zero crossings. We want to prove that for linear combinations of 4 Gaussians, we get at most 6 zero crossings. So, you know, the rest of the thing you can fill in by yourself what the proof by induction is, but let me focus on this case. All right, so the only way I know how to do this is to assert some facts that look a little bit strange at first, but let me demystify them in a second. So, you know, after all, nothing in our argument so far has at all relied on the fact that we're working with mixtures of Gaussians. And now we really have to use the fact that they're mixtures of Gaussians. So Gaussians have lots of wonderful, you know, properties that they're related to a lot of physics types of problems. So one of the things that we're going to use is that there's a notion of convolving by a Gaussian, which will be related to the heat equation. And that's the property that we're going to use to actually prove this ultimately. So let me state, you know, fact 1. This is the crucial fact. This was proved in a paper by Hummel and Gidas in the 70s. And what it says is, given any function, f of x, on the real line, that's analytic, don't worry about it, and has at most n zero crossings, well, we can define a smoothing of that function by convolving by a Gaussian. So let me explain what I mean by this notation. We take f of x, and we convolve it by some Gaussian for any sigma squared greater than 0. Well, you can think about this equivalently as the way that you're defining this convolution operation, for those of you who haven't seen it before, is all you're doing is you're integrating out over some variable z, which takes a Gaussian value. So you're sampling z from a Gaussian, and then you're taking the average of f of x plus z. So one way to think about this is that it's really just the expectation where z comes from the 0 sigma squared Gaussian of f of x plus z. So this is a smoothing operation. You start off with f of x, which is analytic, but what you're doing is you're then averaging f of x over a Gaussian neighborhood to define g of x. Then actually the magical fact is that g of x has at most n zero crossings. So it sounds like we just pulled the fact out of thin air from the 70s, right? Sometimes you have to do that. But actually, I claim that this is actually a very intuitive fact. I mean, it may be a little bit laborious to prove it. You have to use a lot of real analysis terminology to do that. But the way that you should think about this is, what if I gave you some function on the real line and that represented a heat profile in some infinite one-dimensional rod, which then has some permittivity of how fast heat diffuses. And I ask you a question, given that initial distribution of heat on the real line, on that one-dimensional infinite rod, what does it look like at some later time? So that's just the heat equation, which hopefully all of you guys have seen in PDEs, any differential equations class you've taken. But you can actually think about it as the Gaussian is what's called the Green's function of the heat equation, which means if you took a delta function as your initial heat profile, you just had one heat source, and you had this heat spike, and you asked the question, what does it look like at some later time? Then the answer is a Gaussian with some appropriate variance that depends on how much time has elapsed and what your permittivity is for the underlying material. So the same way you can actually express, using the Green's function, what the solution looks like at some later time using the Gaussian, using convolution. You just break up your distribution, your initial heat profile, and you convolve it by Gaussian. It's like treating it as individual little delta functions and then smoothing it with the Gaussian. So you can think about convolution as a smoothing operation that corresponds to allowing f of x to diffuse, or you can think about it as a smoothing operation where I'm averaging over some Gaussian neighborhood. And as I allow time to evolve, I'm actually increasing the width of this Gaussian neighborhood. Now, a lot of things are sort of true once you make this analogy to physics, is that allowing diffusion to happen only smooths the function. It has the property that you can't create new local maxima, because as soon as you try and create a new local maxima in f of x, you're going to have an immediate diffusive pressure to pull that local maxima back down. And you can't create a new local minima because you would have an immediate pressure to pull it back up and smooth it out. So the same way, you actually can't increase the number of zero crossings. So as you convolve by a Gaussian and increase the variance, all you're doing is you're ironing out that function and actually reducing the number of zero crossings, because at worst, two zero crossings can collide with each other and annihilate. So that's what Hummel and Gidas did, is they actually studied what the trajectory is of these zero crossings as you convolve by Gaussian. But it has this nice property that it doesn't increase the number of zero crossings. And this is the property that we're going to use. But we're actually going to run the heat equation backwards. So let's do that. So I'm going to need, yes, now let me keep this part up. All right. And I'm going to need one last fact, so this will be fact 1. And fact 2 is something that is very elementary. It's just that convolution has a nice operation under Gaussians. So when I take two Gaussians, which mean mu1 sigma 1 squared, and I convolve it with another Gaussian, mean 2 sigma 2 squared, then all I get is another Gaussian, where I add up the means, and I add up the variances. So does this fact make sense? Looks intuitively correct to people? Think about it via central limit theorem. We know that the Gaussian is the point that you reach via central limit theorem. And convolution is just like adding up independent random variables and looking at their aggregate distribution. So when I take a very large sum of independent random variables, I reach a Gaussian, and same over here. And obviously, when I add them both up, I also reach a Gaussian, which is why the convolution of two Gaussians is itself a Gaussian. So now we can use these two facts to prove, starting from t equals 3 case, the t equals 4 case. So let's prove that. let's do a proof by picture, so that's a lot easier. So let's take f of x, and let's just let it be the following mixture of two Gaussians. And now let's take f hat of x, which is some other mixture of two Gaussians, which maybe looks like this. So we want to pointwise subtract this function from this function and show that we cross the zero axis at most 6 times. Okay? And we're assuming that it's true for t equals 3 already, that in any linear combination of 3 Gaussians is at most 4 zero crossings. So what I can do is I can look at the smallest variance of any component. Let me call it sigma squared. So all this is just min of sigma 1 squared, sigma 2 squared, sigma 1 hat squared, sigma 2 hat squared. The smallest variance of any component in these 4 components that I'm interested in. And let me subtract off sigma squared from each of their variances. And in this way, what I can get is I get some other linear combination of 4 Gaussians. And as I subtract off something that's closer and closer to the smallest sigma, this approaches a delta function, one of them. And the rest of them just become thinner. But now one of the things I can do is imagine I ignored this delta function, this thing that's just approaching a delta function, as I'm subtracting something closer and closer to sigma squared off from the variances. Well, these guys still have some fixed variance, but this guy is actually localized to some tiny window around it. So if I ignore this guy, I have a linear combination of 3 Gaussians, right? Let me strain my drawing ability and draw it. So what this is going to look like is some sort of function, which will be analytic, which crosses 0 at most 4 times. I guess let me actually draw it this way. So I have at most 4 zero crossings. Now the point is, when I add back in this delta function, I can add at most 2 zero crossings. One on the way up and one on the way down. And now what I can do is I can convolve by n of 0 sigma squared. So fact 1 implies that, fact 2 then implies that I recover the original linear combination of 4 Gaussians. I've subtracted something off from the variance sigma squared, and when I convolve by Gaussian, all I do is I add back in that sigma squared to each of the different components. But now the point is that I can't increase the number of zero crossings. So that's actually what tells me that the number of zero crossings here is at most 6. I don't know, it's getting too complicated to draw. Right? So that's the proof. So you can prove this, obviously this has nothing to do with the case t equals 3 going to t equals 4. Each time what I'm doing is I subtract off the variance of the smallest component, or I subtract off something that approaches that variance so that this becomes like a delta function. And then what it affects is localized entirely to this region. It's tiny outside this region, so it can't really affect the function outside of it by much. It's not going to create new zero crossings. And this way I add 2 zero crossings and I convolve back by the original Gaussian to run the heat equation forwards to recover the original linear combination which now has at most 2 additional zero crossings. So this is actually the explanation for why 6 moments suffice, is just because anytime I subtract f of x from, f of x minus f hat of x, I'm going to get a function that looks like this. And all I'm going to do is I'm going to fit a degree 6 polynomial to the sign difference, and that's going to correlate to something non-zero, which implies that they have to differ on one of their first 6 moments. That was the earlier lemma that we proved. So are there any questions about this proof? The rest of it's making it quantitative, but this is how the argument works.
So I guess there's something about the curvature of the Gaussian that allows for this, right? Is there a name for it?
You could think about it as the curvature of the heat equation, for which it's the Green's function. So it really is a statement that locally you cannot create any local maximum because it has to do with the curvature of it. You can't create new local minimum because you have an immediate local pressure to have that property. So that's exactly the fact that we're using when we use fact 1, is it's really a property of the heat equation. What we're doing is we're taking this thing that we want to reason about, and we're running the heat equation in reverse until one of the components becomes very easy to reason about in such a way that we really can reason about it, and then we're running the heat equation forwards. So the funny thing is that this is actually quantitatively how you reason about Pearson's 6-moment test, is you just quantitatively run the heat equation backwards and forwards and actually measure, and quantify how different their parameters need to be. So it's easy to relate the first 6 moments here to the first 6 moments here, and that way you get a quantitative map between how a discrepancy in moments is related to discrepancy in moments here. The harder part then is actually showing that that you can actually find this degree 6 polynomial that correlates differently in this space, because this is a space which, if you think about it, running the heat equation backwards, these two obviously have large total variation distance with each other. But as I convolve, they actually get a lot closer to each other. But you can reason about their total variation distance by proxy through the moments. Was there another question?
How easy is it to see the base case t equals 3? Is that obvious?
Yeah, so I would do it the same way. That I would start off with 3 things. So even then, right? So 1, it's obvious that it doesn't cross 0 anywhere because it's strictly positive. And then whenever I have a positive and negative combination of 2 different Gaussians, then all I'm going to do is do the same thing and add back in a delta function. You can add at most 2. If the original thing was positive, you subtract that delta function and add 2 crossings, convolve to get back the original one. And you're doing the same argument to go from 1 to 2 to 3 to 4 and so on, is you're just using this, right? The other point is I claim this is also tight. So can anyone see the example that makes this tight? How would I add the delta functions to make sure that when I add up 2 Gaussians and subtract 2, that I actually do get 6 zero crossings?
You can have one Gaussian and then like a smaller negative one.
Exactly.
Smaller positive one, and then an even smaller.
Exactly. So what I would do is I would take a single Gaussian and add a delta function inside. So I'm adding 2 zero crossings in this part where it's really flat. Then I convolve to bring it apart so that it's really flat here. So then it sort of looks like some really smooth function. And then I add back in a delta function here, convolve it and spread it apart, and keep doing this. So every time I add 1 Gaussian to this linear combination, I really do get 2 more zero crossings. I just don't get 2 from the first one. That's why you get 2t minus 2 from this. We're going to cover that next time when we talk about, so, what's funny is that this relied on, magical properties of the heat equation and Gaussians. Actually, you can prove that for any mixture of components whose moments are themselves polynomials in the parameters you're trying to learn, that it has the property that a finite number of moments suffice. But the funny thing is that the bound is finite, but you don't know what that finite is, because it's going to use algebraic geometry tools which are ineffective. So this is the effective version, is that 6 moments suffice for mixtures of 2 Gaussians, but we're going to see a sort of souped up version of that next time. Any other questions?
But if you do know the number of moments, that's the particular thing you're trying to learn.
Right, but the general, yeah, exactly. So the theorem that we're going to cover next time by Belkin and Sinha works for more general mixtures of components whose moments are polynomials and integers, of which Gaussians obviously fit into. But it'll say a sort of statement that a finite number of moments suffice. But I don't know of any other specializations where an actual finite thing is known, instead of just knowing that it is finite.
So they have no idea what to do.
Yeah, exactly. Because it'll use a provably ineffective tool. So we'll see next time why it's provably ineffective too. But it's provably ineffective for a very good reason. All right, so that actually took a little bit longer than I expected. I think let's break here instead of getting into more details on this. But so next time we'll actually cover the algebraic geometry approach to this, and also discuss a little bit at a high level the different types of learning problems that arise. So this is for the strongest type of learning problem because your goal is to learn the parameters. So there are weaker goals that you can ask for, like you can instead ask just to learn any mixture of 2 Gaussians that's close in total variation distance of the true thing. That's called proper learning. And then improper learning is just learn anything that's close in total variation distance. So those 3 problems, it makes a lot of sense to think about, why one is stronger than the other and to think about the differences between them. But I think it'll be better to table that discussion for another time when everyone's fresh. So we'll do it next time. All right. Yeah.
So that assumption that the expectation squared is wrong, you make that like 50x.
Yes. No, it's fine.
But if you make it less,
You make it 2 for the You just need, so it doesn't change the size of the parameters can be more than one factor. It doesn't actually change any of these arguments about the base. So it's not a big deal. Good question.
So how do you think about like subtracting the new number? Does it make sense like this is one,
I mean, I guess see like the Tyker style, the first question you would ask is why can't there be 2 different mixtures that perfectly agree? And Tyker's approach was to go out in the tails and look for the largest variance. Now the issue there is that to get even a single sample from the tails, I'd obviously be running an exponential time. So somehow I want to isolate the meat of the distribution and say that I find the difference there. And this deconvolution operation has the benefit that, in this new space, if I don't have a component perfectly matching this guy, then their total variation distance is large. Because the only way that you can match, you can match something with a delta function is to have another delta function with exactly the same mean and exactly the same variance. The big issue is that total variation distance here, the lower bound, does not translate to a total variation distance lower bound over there in a very nice way. Having a lower bound on the total variation distance between this guy and this guy does not translate to a total variation distance lower bound between this guy and this guy. But what is true is that a difference in their moments does translate to a difference in the moments. So there's an exact expression for what the effect is on the first 6 moments of convolving by Gaussian. It's just some recurrence that actually involves cumulants again. It's a cumulant generating function recurrence. But that's what allows you to say that a difference in these first 6 moments translates to a noticeable difference in the first 6 moments over there.
So this does correspond to like guessing one of the components to match the 6 moments.
So in reality, the way that we do the argument is you don't actually subtract off sigma squared. You subtract off something which is close enough to sigma squared, so that this actually I can fit, I'll have in those 6 zero crossings, and I can fit some polynomial that realizes their sign difference and is non-negligibly differently correlated. And then I can use the transfer properties of how the difference in the first 6 moments relate here to how they relate over there to show that that difference in moments is captured in the original space. But the issue is that the intuition, at least from my intuition, is that deconvolving and running the equation backwards has the property that now these two things obviously have large total variation distance if they don't match in their components. But the big stumbling block, which makes things tricky, is that a TV lower bound here does not imply a TV lower bound there. It's that you can prove something stronger than a TV lower bound. You prove a difference in their moment lower bound, and that's what translates. I don't know if that answers it, but that's the intuition. Yeah. Do I have like quadruple booked this week?